Okay, so all right, so I guess if Jacopo, do you wanna mention again the December workshop before we start? We have a 1 minute.
Yeah, that's fine.
Thanks.
So yeah, it's my pleasure to announce that the second edition of the Ithaca workshop will take place in Genova, the 20th and 21st of December. So the deadline for talk submission is the 12th of November. And also please consider registering as soon as possible if you want to participate, because places are limited in numbers. But the overall registration deadline is the 26th of November. And talks will be about 30 minutes long. So yeah, I hope to see many of you there.
Okay, thanks for that. So I think we can start. It's my pleasure to introduce Todd Trimble from Western Connecticut State University, our today's second speaker, with a talk entitled Grothendieck Groups of Two Rigs as Lambda Rigs. So please, Todd.
Thank you, Eduardo. And thanks also to Fosco for getting me set up with this. So we'll try to speak loudly so that you can hear. I hope the sound is okay. And do I understand that I have 45 minutes? Is that correct?
That's correct. Yes,
okay.
To leave some time for questions. Yeah.
Okay, great. Okay, let's get started here. So I'll start off with a little bit of background about how we got into this project. I'm going to be speaking about a paper which has been written up recently, which is called Categorified Plethism and Schur Functors by John Baez and Joe Moeller, who is a recent PhD of John Baez, and myself from this year. But this paper was a long time in coming. So, I mean, really, this project started all the way back in 2007, which is almost the beginning of the In Category Cafe. So in 2007, John Baez posted an article asking, what is a Schur functor? So if you ask representation theorists what they think a Schur functor is, you will get some kind of answer. But as you will see, we want to think a little bit more generally about what people might be thinking about. So in traditional terms, a Schur functor is a kind of functor that you can define on complex vector spaces or vector spaces over some other field using more or less colimits and the symmetric monoidal product that you typically have available. So an example of such a Schur functor would be something like the second exterior power, also known as the alternating square functor. So if you don't remember what that is, I can describe it for you. You start off with a vector space V, and you consider two maps, one of which is called sigma here. It's the symmetry map, which permutes tensor factors. And the arrow labeled above would be minus the identity. So what you want to do is you want to force the symmetry to introduce a change of sign, and you do that by passing to the co-equalizer of those two maps, and that lambda squared is the alternating square. So that's a very kind of typical consideration or functor that that goes by the name of Schur functors. They're a little bit more general. These are much studied by representation theorists, and if you begin reading books about this sort of thing, for example, the book by Fulton and Harris, I believe it is, there will be a lot of discussion about Schur functors and how you build them up. So if you look at a traditional account, it gets very much involved with the representation theory of symmetric groups. So you start off with an understanding of how you build up, for example, irreducible representations by means of things called Young diagrams, and there's some interesting combinatorics there. But given such a representation, let's say attached to a Young diagram, what you can do is you can begin to operate on vector spaces. So you can form a functor which will take a vector space V to a co-equalizer, which I'm going to describe right now. So I'm going to describe a tensor product of two, let's say, modules. So over here, we start off with the symmetric group on in letters, and C adjoined that is the group algebra over the complex numbers. V is a complex vector space, and you can let the group algebra act on the vector space just by permuting the tensor factors. So V to the tensor n gives you a left module of the symmetric group. On the other hand, if you have a right module attached to a Young diagram, then you can operate on the right as well. And so you can consider right action tensor V to the n, or you can consider left action on V tensored on the left with SD, this representation. And you form these two arrows, and the effect of passing to the co-equalizer is you can sort of swap the actions of the symmetric group on either side of the tensor symbol here. So that gives you a very general kind of flavor for what Schur functors look like. So they send V to this type of thing right here, and you can get a little bit more general. I mean, these are the Young diagrams give you irreducible representations, but we can do the same thing for any representation. So I think my screen might be a little bit small. Anyway, back in 2007, this is what John was reporting, how he got started on this blog article. He has a friend named Alan Knudsen, who is, I believe, a representation theorist or a distinguished algebraist. And he had mentioned that he had always thought of Schur functors as being functors on complex vector spaces. But by way of introducing this blog post, John quotes Alan as asking, I presume an email, there's this Alan Knudsen speaking, for as long as I've understood Schur functors, I've thought about them as functors on complex vector spaces. But now that we're going through them in a reading course on Fulton's Young tableaus, I discovered that the input isn't really a complex vector space, but an arbitrary module over a commutative ring, and maybe, just maybe, a bimodule over a non-commutative one, but I doubt it. In particular, the Schur functor commutes with base change, aka, or also known as extension of scalars. Then he asks, what is the right way to describe this object? What is the right way to describe a Schur functor categorically? Or should I say 2 or 3 categorically? So that's the question he puts out to John. And John had a more or less immediate response that needed to be fleshed out a little bit more, but roughly speaking, John's impression was that you should think about Schur functors very generally as consisting of a family of functors, more or less one for every type of categorical structure which will support the constructions that we just looked at. So you need to have a symmetric monoidal. It says Zoom cannot detect my microphone. Okay, I hope you can hear me. So if you have a symmetric monoidal functor, and if you have enough co-limits to work with, let's say, for the sake of argument, an abelian category, possibly vectin rich, so we can talk about vector space representations, then more or less this should be enough of an environment in which you can define a Schur functor. So that was his rough impression about the way this should work. But not just a family of functors. I mean, we should have actually a natural, or in 2 categorical language, a pseudo-natural family of functors. And what that means is that Schur functors should commute, like Knudsen said, they should commute with change of base. Meaning this: if you have a functor f, I keep getting this message that it can't detect my microphone. I'll try to ignore it. If f is a symmetric monoidal functor and preserves, let's say, enough co-limits, then it should be that this type of functor will transform Schur functors appropriately in the sense of a canonical isomorphism between these 2 ways. This is expressed by means of a commutative square, or I should perhaps say a commutative square that commutes up to isomorphism. Let's see, so where are we here? So John then made a very bold conjecture about what a Schur-functor really is. So he said an abstract Schur-functor should be the same thing as one of these pseudo-natural transformations. Going from U stands for the underlying or forgetful functor, which will take whatever types of categorical structures you envisage as supporting Schur-functors, mapping to cat. So I put little question marks here to say, well, you might want to think about exactly what you want to put here. I'm just going to use this as a placeholder for now. But abstract Schur-functors, according to John, should be a pseudo-natural transformation between U and itself. So if you write out what that means, if you write out the structural constraints for a pseudo-natural transformation, you will get this type of square commuting up to isomorphism. This lambda here means a generic Schur-functor here, like the exterior square. And this stands for the underlying functor of a symmetric monoidal colimit preserving functor. So something along these lines. Okay. I'm sorry, I'm having trouble with my thing. Let me try again. No. I'm sorry, I'm having some trouble here. There we go. Okay. So let's consider some examples beyond complex vector spaces in which it makes sense to define Schur-functors. Easy example, category of finite vector spaces. That's almost a given. A more interesting example is where you consider vector space representations for any group G. And I think for many purposes, people stick to finite dimensional vector spaces for various reasons. You might want to consider a Grothendieck group or something where that makes the most sense. Category of supervector spaces, or if you start off with one of these categories, you can form this super things in that category that will also give you a supporting environment for Schur-functors. I should mention supervector spaces. What are they? As long as you know what chain complexes are, then these are Z mod 2 graded chain complexes. So there you go. Algebraic geometers consider coherent sheaves. Lastly, I'm looking at the category of vector bundles over a topological space. It's a very classical environment in which you consider things like alternating squares or symmetric powers. You perform these various constructions in K-theory, for example. So this last example is absolutely an example we want to consider. Trouble is that this last example does not admit all finite colimits. In particular, one can show using simple examples that the category of vector bundles does not admit all co-kernels of maps. So that is to say that going back a little bit to this slide here, maybe we ought to reconsider what we're putting down here. So let's not use this, but let's think a little bit more generally about what might be involved. So whatever this thing is that we want to use in place of symmetric nodal abelian categories, I'm going to call it a 2-rig. Okay. And going back now to vector bundles, all right, doesn't have all co-kernels of maps, but what it does have is it admits splittings of idempotent maps. So that will be very important for our purposes. So as long as the map is idempotent, you can construct the co-kernel of it. And continuing this thought, if we want to get our hands on things like the irreducible representations for Young diagrams, as long as you're working over characteristic 0, you can actually obtain all of these by splitting certain idempotents. So all of these irreducible representations arise by means of constructing an appropriate idempotent element, typically constructed by using a symmetrizing operator, And again, forming the co-equalizer of these two maps, where one is multiplication by the idempotent, other is the identity map, and the co-equalizer will in fact be the image of pi d acting on this group algebra. So you get all the irreducible representations anyway, even if you just restrict to these idempotent splittings. And so eventually, I mean, this took a little bit of time, but eventually I think I had proposed that we actually take our notion of two rigs as being exactly this. So work with symmetric monoidal categories in the sense of vect-enriched functors, and make sure that they're Cauchy complete, which for the vector space enriched categories comes down to saying that it has finite coproducts and it admits splitting of idempotents. So that is for us what a two rig will be, no matter what other people think a two rig is. This feels like a right notion in which to get work, which to get busy. Okay. So the first thing is yes, we can define Schur functors now on any two rig. But to make further progress, we should maybe think a little bit about the nature of this forgetful functor or underlying functor. And one nice fact, which is going to sort of tie us into the very classical study of symmetric group representations, is the fact that this functor is representable. So let me back up a little bit, and let's go back to our sort of placeholder that we had here. It may not be so clear what symmetric monoidal whatevers have to do with the classical theory of symmetric group representations. It's not absolutely clear, but when we begin to study the representability question, it will become quite clear what the connection is. So let's think about how this works. So when we're talking about two rigs, one is gutted by a very strong analogy with ordinary one rigs, meaning what? Meaning a structure which is ring-like, except that you don't assume that you can take negatives of elements. So that's the notion of one rig, and we're going to be guided by how one can construct free one rigs in order to understand how to construct in a categorified way free two rigs. So thinking about the free one rig, we'll come to that in just a minute. We can, in fact, we're going to be able to construct the free two rig on any category, but we're going to study a particular one for this talk. So you can construct a left two adjoint F, which is the free two rig. Assuming we know how to do that, we can show that this forgetful functor is representable quite easily. So the forgetful functor can be considered as being isomorphic to what you get by applying cat1 blank, which will map cat to cat, let's say. It's just really cat1 comma blank is the representing the identity functor, and so you get this isomorphism here. But if U has a left adjoint, then this F can be applied to this side right here, and voila, you see that U is being represented by this free category on one object. So yeah, the free two rig on one is the star of the show here, and I want to go through and describe how you would actually construct that. Okay, the way the construction is going to work is going to be very parallel to how we construct the free two rig. The free rig on a terminal set. What is that? Well, that's going to be like a polynomial algebra, except that the coefficients will be natural numbers and not integers. So the way you can think about that is to think about how do you build up polynomials from the point of view of high school algebra. So you start off with the notion of monomials, and then you begin adding them up freely to form polynomials. So let's start with the monomial case. That means that we're going to construct a multiplicative monoid, in fact, the free multiplicative monoid. And then we're going to take that idea and apply it to the two categorical case. So we're going to construct a free 2-rig by starting multiplicatively and taking the free multiplicative part, which is the symmetric monoidal structure. We'll take the free symmetric monoidal category on the terminal object, and as many people know, this free symmetric monoidal category is the groupoid of finite sets and permutations. So already you begin to see the symmetric groups popping out of that free construction. The monoidal product here is intuitively just kind of putting two sets together, much like a coproduct, except that you're restricting the coproduct on finite sets to the subcategory consisting of isomorphisms. We call that the groupoidal core. So that's the free symmetric monoidal category on one element. And now we begin to form the polynomials. So we're going to now add in the additive structure freely. So the additive structure, in the way I'm thinking about it, what we do is we want to first move over to the context of vector space enriched categories. There's a tried and true way of doing that. If you have an ordinary category, meaning enriched in the category of sets, then you can always change base as long as you have a halfway decent category like vect in which you can construct a free functor. So this is the way you change base so that you get a vector space enriched category on, in this case, the objects here are finite sets or integers. So this is a change of base of enrichment. And then you begin, we want to have all the Cauchy colimits or the absolute colimits. So we adjoin finite coproducts. And the way you do that is you can think of it this way. You take your vect enriched category, you can embed it, if you like, into a enriched pre-sheaf category, and then close up. You got this thing embedded in here, and then just take the closure of this embedded category under finite coproducts. So just sort of taking sums that way. And finally, what we want to do is we want to split the idempotence, as we know. So split the idempotence in the finite coproduct completion, and when you've done all that, then you have constructed the free 2-rig on a single element. Okay. And we would like to think about these as being something like polynomial functors. So we're going to give this a name, parallel to how we call the free rig, we call that the polynomial algebra in adjoin X. What plays the role of the natural numbers here are finite dimensional vector spaces. So I want to call this category, this free 2-rig, I want to call it vec adjoin X. Vec consisting of finite dimensional vector spaces. And to think about what vec looks like, yeah, you can think of these as being finite direct sums of irreducible representations of symmetric groups. Or if you are familiar with the language of Joyal species, you can consider these things as being finitary species valued in finite dimensional vector spaces. So species are functors out of the permutation groupoid. Being finitary is polynomial species. I hope you all can hear me. Can somebody give me a thumbs up that you can hear me? So, okay, thanks. All right. Now we're going to go back to this idea that John had, which is to consider Schur functors or abstract Schur functors as no more and no less than pseudonatural transformations from the forgetful functor to cat, from, that is to say, pseudonatural transformations from U to U. And now that we know that U is representable in this way by vec X, we can replace U by this representable 2 functor here and consider pseudonatural transformations from this representable to itself. That would be the same thing. So this symbol here means a categorical equivalence. All these things are categories here. Okay, so we are thinking two categorically at this point, as Knudsen surmised that we might have to do. There's a Unida lemma for two-category theory, in which you can say that pseudo-natural transformations between representables can be boiled down to ordinary maps from the representing object to itself. So in this case, we're considering two rig maps from vec x to itself. And vec x being the representing object for the forgetful functor, this means that what we are doing in essence is taking the underlying category. This construction here is the underlying category of the category of polynomial species. So underlying category like that. And what's really nice about this, I mean, this is a kind of game that you can play no matter when you're talking about a free object on one element. There are certain games that you can play with that. It comes up in ordinary algebraic theories. But a game that you can play is that, unary operations, you can think of these pseudo-natural transformations as being the definable functors that are available on two rigs. So any two rig will support such a pseudo-natural transformation, or rather and I'm still getting these messages about the sound. It's getting in my way. But we're saying that these definable unary operations are codified by objects in the representing category. That means in turn that we can contemplate the composition of pseudo-natural transformations. So you have two transformations from U to U and you compose them. That will give a monoidal product. And since we have a categorical equivalence with polynomial species here, you can transport across the equivalence the monoidal structure that you have here by composition to some other monoidal structure on polynomial species. And people name this various things. Joe and John and I have taken to calling this the plethistic monoidal product, in honor of this notion of plethism that is very important to representation theorists. But if you're more familiar with Joyal's species, then you might call this the substitution product. So that is in fact what this is. So substitution product on finite species. Plethism looms quite large here. So where we are going with this is we are going to be marching into the neighborhood of lambda rings as advertised in my talk. So we are considering these polynomial functors, and these form what is also called the representation ring of the symmetric groups. And well, I should back up a little bit. The representation ring is gotten by, yes, taking these polynomial functors and considering them up to isomorphism. So isomorphism classes give you a rig object, and then you form a ring out of that by the familiar Grothendieck construction. And that could be called, I'm going to loosely call it the K theory of this two rig here. It's really K naught. But when you begin to study this representation ring and its inner structure, that actually gives rise to the theory of lambda rings, where the principal operation is the so-called plethism. So I'll talk a little bit about that, and trying to keep in mind that I have 45 minutes. Okay, so we start off. We're going to sort of go in two steps here. First, before we get to K, I'm going to call it J. J of this two rig of polynomial species will be the set of isomorphism classes of polynomial species. So it's a set, it's a small set, but it also comes equipped with rig structure, which is induced by the two rig structure that you have available on species. So in other words, the multiplication of this rig of isomorphism classes is induced by taking the symmetric monoidal product. So that descends through isomorphism classes. And then you also have coproducts or byproducts, and that will give you, when you descend through isomorphism classes, that will give you the addition structure. So you get a rig structure in that way. And people come up with various names for what to call this. The very famous representation ring called lambda has inside of it a rig consisting of what are called classes of positive Schur-functors. What one ultimately does, though, is one doesn't just rest with a rig called JR, but rather one ringifies it by freely adjoining negatives. So the actual object of interest, which I'm calling K of vect X, is what you get by taking the free ring on this rig, free in the sense of being a relative left adjoint, but what it means in sort of common sense terms is that you're adjoining negatives in the appropriate relative free way. So just adjoin negatives here. And I mean, I'm looking at the case where I'm taking my 2 rig to be polynomial species, but really the same constructions work for any 2 rig here. You get from a 2 rig, you get a rig, and from there you get a ring by taking this is called the Grothendieck construction. Okay. And one of the big theorems here, I say that the representation ring carries an awful lot of structure here, which is of enormous interest in various branches of mathematics. Various people have packaged the structure that it carries in terms of a structure called a plethory, which I'm going to describe kind of quickly. But a plethory is a very special kind of algebraic theory, and the algebras of this are, in fact, the lambda rings. So I will describe in somewhat brief, sketchy terms what is meant by a plethory and try to sketch where this plethory comes from at the higher categorified level of 2 rigs. So what is a plethory? A plethory consists of a commutative ring. Our main object of interest is the ring which I've been calling lambda, the representation ring, but with a lot more structure. So it's a ring, yes. Don't call it B for the time being. It's a ring which would give you a representable functor, mapping from rings to sets. But the kinds of structure that turns out to be available allows you to construct an actual lift of this representable through the forgetful functor so as to get an endofunctor on the category of rings. I wasn't going to describe in great detail what this kind of structure is, but it's called a biring. If a ring and its representable admits such a lift, then the ring plus this lift gives you a biring, and this is sort of an important piece of the puzzle about what a plethory is. But moreover, not only do we have this lift, do we assume that it comes equipped with a lift like this, but you assume more about this lift. So a plethory consists of such an endofunctor lift together with a comonad structure. Now, I want to talk a little bit about that. In the first place, one can prove that any lift through this forgetful functor, any lift of a representable will turn out to be a right adjoint. So it's not just any endofunctor that we would get if we have a lift at all. It's not just any old functor, but it'll actually be a right adjoint. So it'll kind of work both ways. If you have a right adjoint endofunctor like this, you can follow by this forgetful functor, which is a right adjoint, and you get a right adjoint from here to here. Such adjoints must be representable. And conversely, if you have a representable and can lift it, that will be a right adjoint. Okay, so really what I'm driving at is that a plethory is no more and no less than a right adjoint comonad on the category of rings. I should mention, by the way, that in my opinion, this notion of plethory is already too specialized because you're concentrating very much on commutative rings here. You don't really, for any variety of algebras, for any algebraic category over sets, you can consider, you can have similar considerations about lifting of representables and so forth and so on. And you can define a plethory in this general context as being any right adjoint comonad that exists on the category of algebras that you're interested in. That I think is the better notion. But while we're on this topic of right adjoint comonads, there's a little piece of categorical lore here that says that if you have a comonad, which is a right adjoint, and then if you consider its left adjoint, then there will automatically be a monad structure on the left adjoint. And moreover, in some sense, these right adjoint comonads and their left adjoint monads are basically the same thing from the standpoint of their semantics. So the kind of key result here is, and this goes back to Eilenberg and Moore all the way back in 1965, is that the category of coalgebras over the comonad turns out to be naturally equivalent to the category of algebras over the left adjoint monad. Whenever you're in that situation, you really are in the neighborhood of this plethory in the generalized sense that I'm speaking of. So I want to spend a little bit of time getting a little bit more down to earth about what is at stake when we have this this right adjoint comonad. So I'm asking concretely, what does this give us? What does this buy us if we have a comonad structure? Well, okay, this is a endofunctor on rings, but I'm going to begin bringing it more down to earth just by descending down to sets. So I'm going to forget for the moment the ring structure here and apply U just to see what happens, bearing in mind that the composite of U with this endofunctor is representable. So U following phi is this representable functor given by the underlying ring in this case. And then on this other side, we have U phi phi. So I'm starting off with the co-multiplication. I apply U, and the codomain here is U phi following phi. That would be the representable following phi here. So that this transformation is tantamount to a transformation of this form here. And already we're getting a little bit more concrete. So what we have here is a map, a transformation out of a representable functor. There's a Unida lemma, which will tell us that maps out of the representable into a functor are in one-to-one correspondence with elements of that functor applied to the representing object B. So we were talking about elements of Hom B, phi B, which of course are nothing more than maps. This is a ring map. So this lives up in rings for right now. This is a ring homomorphism. But we can consider continuing to bring this down to earth. So we can apply the underlying set functor again. So hitting it on the left here, you get UB. Hitting it on the right, you get U phi B. And U phi being representable, you make it even more down to earth. You have a function now into the set of ring homomorphisms from B to B. And you can go further. So you can follow that by the map, which expresses the fact that U is a functor, and you get a map from UB into functions from UB to UB. And by a currying mechanism, you can think of this as a binary operation on UB. And that is the same thing as what people call plethism. So the main point here is that the plethism that I spoke about in the two categorical case descends down to plethism at this riggy or ringy level, and that corresponds to the co-multiplication of the plethory. Okay, kind of wrapping it up here in a few minutes. Right. So I am going to take a little bit of a shortcut here. It's a little bit difficult to describe in detail the nature of the plethory on the ring lambda, but as a stopgap, I'll look at the nature of plethism on the positive part of the representation ring. So this comes by taking isomorphism classes of the free 2-rig or polynomial species. So some notation here. If C is a 2 category, yeah, I want to descend now, begin making my descent into the land of 1 categories. I want to decategorify here. So my first step will be if you have a 2 category, like the 2 category of 2 rigs, then you can make a change of base. So you can, if you think of a 2 category as being enriched in cat, then you can change base by applying a change of base functor from cats to sets. And the result will be a 1 category here, which I'm calling C ho, ho standing for homotopy. So the category here is defined as having the same objects as the 2 category, but the morphisms of C ho are the 2 isomorphism classes of the 1 cells that you have in the 2 category. That's a very famous way of decategorifying a 2 category to get a 1 category. Okay, and then we have this J functor, which is valued in rigs. So for any 2 rig, you can take its isomorphism classes and you get a nice little functor here from the homotopy category, the 2 rig into rig. And this will have some nice properties, like it'll preserve products and some other things. And what we're going to do, I'll tell you where I'm heading with this. What I am trying to do is I am trying to construct, just one moment here, I am trying to construct a rig analog of this plethism function in a series of steps. So this HOM will be the set of rig morphisms from lambda plus to itself. And I'm trying to construct what will play the role of plethism at the level of the representation rig. Okay. So how do we do it? Okay, so let's just recall that vec x is representing the underlying functor. So you have a canonical equivalence between the underlying category and the category of 2 rig maps like this. And now so this is a map between categories. This is a functor. Let's pass to cat ho. So we're just going to consider it a 1 cell in an ordinary vanilla category. Cat ho is not a 2 category now, but a 1 category. So we'll interpret this as a 1 cell here. And now we're going to hit this arrow, this 1 cell. We're going to hit it with this functor, which will map into the category of sets, so that we actually get a map between sets going from the underlying set of lambda plus to the 2 rig ho from the polynomial species into R. Okay, and that's just what happens when you hit it with cat ho. And then you can further apply the fact that you have this functor J, use the fact that J is a functor to map from this HOM over into this HOM, and then consider the composite here, and that gives you exactly the plethism that I'm after. So it gives you a map from the underlying set of lambda plus to the set of rig maps, and that is the plethism, which is something like, as I said before, it's something like a substitution product. You're substituting one representation into another, and that's what plethism is about. So in the end, this will give you the data for a code multiplication on the Comonad. And when all is said and done, I am just about out of time, but through a longish series of steps, which is described in our paper, one constructs a right adjoint comonad, which here will be a comonad on the category of ordinary rigs, calling that phi plus. And the fact of the matter is that For any 2-rig R, we get a map then from the representation rig to this comonad applied to this representation rig, and this will be a coalgebra structure for phi plus. That coalgebra structure is the same thing as an algebra structure for the left adjoint, and that is the same thing as a lambda rig. If you want to take this a little bit further, then you can jack this up a little bit more to the context of lambda rings. But this gives a sort of thumbnail sketch about why you should expect that if you start off with any 2-rig and then decategorify it, then you will wind up with a lambda ring, or a lambda rig in this case. So that is about all the time that we have. The paper that we have written is on the archive. It is over 50 pages long, and I am in no position to do it any real justice. So this is just a little taste. But in particular, one of the takeaways is why 2-rigs, in the sense of Cauchy complete vector space enriched symmetric nodal categories, is maybe the right context in which to think about Schur functors, and in which to think about the lambda rings that arise in that context. So I'm going to let that be all for now. It is 10:15 on the dot, and I really thank you for your attention. So.
Thank you. Thank you, Todd, for the talk. Are there any questions? If there are any, just
I have one question.
Yep.
I have one question. So Todd, at some point you said that most of these constructions can be done for modules over a ring, but then you said that your definition of rig is based on vector spaces. So why vector spaces? So enrichment over vector spaces. Why vector spaces and not modules over a ring?
One can certainly contemplate working more generally. I was thinking of Schur functors as the constructions that you get by taking an irreducible representation of a symmetric group and then letting that operate in some way by an unary operation. So it's the fact that the representation ring consists of vector space representations that sort of guided that particular move. But by all means, I mean, I would say let a thousand flowers bloom, and you're certainly free to consider much wider contexts. But this is the classical context in where people study things like K theory and characteristic classes and so forth. And so we set our aim to be a little bit modest here, with a possibility of expanding out in directions such as what you're suggesting. So yeah.
Okay. Are there other questions for Todd?
I would like to ask a question. Hi, Todd. Thank you for your talk, and very interesting and difficult for me. I have to study many things to understand all of it, but maybe I got an idea of the big picture, and this is very, very interesting. My question is not really a question, it's a sort of curiosity. Some time ago, I came across an interesting PhD thesis of a student of Enrico Vitale about the Grothendieck 2 group, the construction of the Grothendieck 2 group. And I was wondering if you are aware of it, and maybe if it is related somehow with your work now that you told us today.
That sounds really intriguing, but I'm not sure that it intrigues me in the way that was intended by the student of Vitale. So there's a problem that comes up that we really had to grapple with, which is the fact that if you start off with a category with coproducts, as we are, and attempt to categorically adjoin negatives, you really can't do it.
Yes, yes, yes.
So I don't know whether Vitali's student is talking about
The student is, by
workarounds
the
for
way,
this.
I have to be Corentin Dragman. Corentin, the name
Okay.
of the students.
Would you be able to write that down in chat so I can see it? So.
I can send you the references. I don't know if it was been published in the paper, but
Okay.
the thesis is available. I can give you the link. I can put it in on the chat here if you're interested.
Yeah.
But of course, you're right. I mean, he works with inverses somehow because the idea is to categorify two groups, and so you add inverses.
Yeah, I mean, I've thought about this quite a lot, and I mean, in the representation ring, one considers what are called virtual classes, where one formally takes a difference between isomorphism classes of, representations. And so this is not thoroughgoingly categorical, but there are lots of neat little tricks that come up involving things like the Euler formula. So the Euler formula says that the virtual difference H0 minus H1 is equivalent to the virtual difference between C0 and C1, where these are the components of a Z mod 2 graded chain complex. And so one has little workarounds if one is willing to sort of lift up to the level of differential supervector spaces. One can kind of get around some of these difficulties involving this problem of negatives. So, I've thought about how you might try to formalize that in terms of, I don't know, something like the homotopy category of a, what's the word I'm looking for? A Aquilin model structure on differential supervector spaces. So there are various technical tricks that I learned from Joyal, which would allow you to certain workarounds, but I'm not sure that's what this student is pursuing. I don't know.
Thank you. I've put the link on the chat.
Terrific.
The
All
reference, yeah.
Chat. Drugmond. Okay. Terrific. All right, let me just open that thing. Beautiful. Thank you so much.
Welcome.
Okay, do we have other questions?
Yes, if I can, I have a question. It's not a technical question, but I would like to know if you, John and Joe, have something else in like as a work in progress to.
In the works?
Yes.
I think I saw Joe here a little while ago, so he might want to weigh in too. But we are. It's a bit rambling, but right now what we are studying are Adams operations, which are very closely related to lambda rings. So
Yes.
I mean, when you pass to lambda rings, there are certain auxiliary operations that you can form, which are hard to categorify for roughly the same reasons that we were just discussing. But
So
these
you
are
want
called
to
Adams
yes.
operations, and we're trying to
Mhm.
connect that up with things like the study of F1, with the Frobenius maps of various types. Eventually, we would like to look at things like how people are trying to approach the Riemann hypothesis via descent to F1 from spec Z to spec F1. So we are sort of slowly wending our way and getting a deeper understanding of the structure of this lambda with certain other auxiliary operations in mind. So Joyal has studied a related structure, which is in some ways simpler, called delta rings, and he concentrates on one Adams operation at a time. And so it'd be nice to develop a thoroughgoing categorical understanding of where these things come from, in the same way that the representation ring comes from two rigs in some sense. So we're just feeling our way into it right now. And if Joe is here, I would invite him to say a little bit more, but I thought I saw him.
when you categorify also the Steenrod algebra, give me a call.
Yeah. Oh, okay. If you're studying that, yeah.
No, I mean, I remember that part of algebraic topology, the little algebraic topology that I learned. And that was interesting. That was, I remember having a hard time giving a sense on what are they called? Adem relations?
Yes. I mean,
yeah.
you're talking about characteristic classes. And
Yeah.
I mean, these characteristic classes are really tied up with, I mean, there are lots of ways in which you can think about what is the representation ring. So combinatorialists have a way of thinking about this as a ring of symmetric functions. So it's very combinatorial. Then you have the K-theorists or the algebraic topologists who think in terms of characteristic classes on classifying bundles. And that's something else. But so you have maybe 5 or 6 different ways in which to think. And then you have the representation theorists. So you have 5 or 6 different ways of thinking about what is this lambda. And I mean, certainly these Steenrod operations will arise one way or another. So
Yes.
I will keep you posted, though. So we'll start heading in that direction. So.
We have to also get back at our work at some point.
We do. Fosco, I think about it all the time. I think about it all the time. It's just I need to kind of put finger to typewriter or keyboard.
Yeah. Okay, let's have a call soon, like next week or.
Yeah.
Okay.
Yeah.
Thanks again.
This week has been very busy, but things are opening up. So yeah, let's do it.
Okay. Thanks again.
Thank you.
Okay, I think we can end the session here and then continue with comments or chats afterwards as usual. So let me thank Todd again also for the several answers that he gave. And yeah, so I guess we can stop recording.
Okay.
And yeah, whoever wants to remain and have a chat is